Okay. Yeah. Let's get started. And today we will talk more about quantum algorithms. And so this time we talk to, let me see. Do we finish this? Oh, yeah, I think we actually finished Bernstein was running algorithm, right? Okay, and then I guess today we will, can stop short. We will finish this slide today. Okay, and anyway, recap, we are on quantum algorithms. So we start with, so first we define this idea of quantum black box. So we have this box that compute a function, and so you have an input register and output register, and this black box it will read what's the input register and write down to the output register. So you have x and you have y plus f of x here. Yeah. So this is like a quantum black box. And yeah, so we start with Dirichlet's algorithm. So we start on those black box algorithms, and we see that we have this Dirichlet's algorithm, which can calculate something about your black box faster than classical algorithm can be. So we see that with this Dirichlet's algorithm, which only uses one box here, you can calculate f0 plus f1, where f is a 1B function. And this is not possible classically because you need to put two boxes inside your classical algorithm to calculate f0 plus f1. And here we use crucially this phase kickback technique, where we actually do something on the output register. So we put a minus on the output register. Then we see that on the input register, so if we put a minus there on the output register, then we see that what happened is the value of this function become something on this phase. So we have minus 1 to the f of x times the input state. So the information about this function small f goes to exponent of this phase here. And this is a phase kickback. And we can think about this phase vector is actually on the input register. And then we do header map, we can distinguish in the plus state and the minus state. Okay. So that's Dirichlet's algorithm. And then we have actually three algorithms that all use the same idea. Then we have Dirichlet's algorithm, which generalizes the Dirichlet's algorithm by just having more bits in input. So we have n bits here and n bits here. And but here we need some promise on our problem. So we promise that our f of x is either this constant function, either this constant function or balanced function. Constant means output is always 0 or 1, and balance means that when you look at the truth table, there are same number of input give 0 as output, and so number of input which give 0 as output is same as the number of input that give 1 as output. Okay. So this is Dirichlet's algorithm, and we run through the same circuit, but with more bits on the more bits on the input register. Then we see that when we measure the output, then we can just then we measure the output, we get an NB string, and from that NB string we will decide whether our f is small f is balanced or constant. And we see that we have this special property that if you do the calculation carefully, you see that when z is O0, then then this small f must be constant. And also when small f is balanced, you will never get a probability, you will never get the output being z or equal to 0. Okay. And in the middle, we have this nice identity or nice formula we derive. That is, we see what is header map to the n on an NB string. And we see the result is you sum over all computational basis with some phase vector. and the normalization, and the phase factor being -1 to the x inner product with z, where x is this input string here, and z is the output string here. So this is NB string, this is output string. And when we say inner product, we think this as the bitwise inner product between two n-dimensional vectors. So x dot z is x1 plus times z1 plus x2 times z2 all the way to plus xn times zn. Okay. And this is a number you can do mod2 or not because it's -1 to the power. And I guess for now the notation is when we write inner product is it's a bit confusing, but I guess for the notation here we mean it's just an integer, not necessarily less than 2. Okay. And so this is the very nice formula that we can use a lot of time, and we immediately see that in the next algorithm, bursting was a running algorithm. We also use the basic same circuit to calculate another problem. Now we also have promise problem, but now we are no longer in decision problem. We try to find a B string. Okay. So here the promise, we also have promise on our small f, and we are promised that small f is determined by a secret string s. Okay, so s for secret, and we say f of x equal to, so f of x is still a bit, is s inner product with x, then take mod 2. Okay. So so the inner product is just like the inner product we do here. We take s is NB string and x is also an NB string. So we take each element of those string and multiplying them together and adding them together. You get a number, then you take mod 2. This is f of x. Okay. And so classically we can learn s in n-query, and you can show that you cannot know s by basically less than n-query. And quantally, then we also run this Diotritos algorithm circuit, and we see that because we set up f nicely, and so when we do measurement at end, so we get an NB outcome. This NB outcome is actually just the secret string as we try to find, okay? Because we have this nice thing here. Now f of x is x inner product with s. And so when we do this, this is -1 to the z dot s z plus s inner product with x, and we see that this thing is and when you sum over oz, when you sum over ox, then this thing is 1 if only if z equal to s. When z don't equal to s, this thing is going to be 0 because there is going to be cancellation between different x. Okay, and so we have this thing, and so we see that presently was running algorithm give us NB outcome, and with just one query to U of f, which is a bit surprising, but this is true. So one quantum query gives us NB, the classic NB the information. Okay, because we can read the information out of the input register. It's something funny with the quantum query. Okay, and now we talk. I guess we talk very roughly about query complexity. And we talk about quantum query complexity. So we see that in all these algorithms, now we are dealing with query algorithm. It's a bit different from usual classical algorithm. Usual algorithm we think about, because when we talk about circuit model, we think about an algorithm. We have some input, we put some gates, and then we measure some output. Okay. But for those query algorithms, the input are not really the states you feed on the left-hand side. The input are actually those black box. Okay? And as we say, when we talk about black box model, there are two things that are called inputs, and it's a bit confusing. So we sometimes think those black box are computing a function, and obviously those function has an input. But we also think the truth table of the whole truth table of this function also as an input to our query algorithm. Okay? So this is like you can think of this like a nested algorithm. So we have a higher algorithm that we try to compute something on those black box, and the black box themselves are another function. Okay, so there are two layers. Okay, and to the higher layer of the algorithm, so those Bresney-Vazirani algorithm, Dirichlet algorithm, or just a Dirichlet algorithm. Okay, those algorithms, their input are the black box. So like the subfunction they are calling is actually their input. And so we think the truth table of f of x as the input to our algorithm. Okay, and now we define this query complexity as the minimum number of those black box. So number of query you need to use in your algorithm to determine to determine your bigger problem. So maybe to say in Bresney-Vazirani algorithm, your problem is to determine the hidden edge of your black box. Okay, so in those query algorithm, you are trying to learn something on your black box. Okay, and yeah, so we are asking that how many questions you need to ask this black box to learn some property of this black box. Okay. And for the easiest example, in the Dirichlet algorithm, you are trying to find f0 plus f1. Okay? And yeah, but in the question, you only try to find just this information, so you can know nothing else. Okay. So you only need to, for example, in Dirichlet algorithm, we see that the kind of the trick here is you only learn f0 plus f1. And so you don't need to know f0 and you don't need to know f1, but you only need to know their sum. Yep. And yeah, so this is quantum query complexity. You can define quantum query complexity for every function. For every function you want to calculate on this small f. Okay, so you can ask also the question. So for example, here we ask f0 plus f1. And yeah, we can ask is there a 0 or not, etc. Okay. And the minimum number of query you need to use to determine this property is called quantum query complexity of your problem. You're something about f. Okay. And yeah, so you think about quantum algorithm, query algorithm, and then it's beware the input are all 0. And the actual input are the black box. So you will do something, you will ask the black box several times and do unitaries that's independent of your small f. And in the end, you do measurement and try to calculate something about your small f. Okay. And in this picture, then the quantum query complexity will be the number layer here. Okay. And as we said, we want to study this because this is like a modular way to view your quantum algorithms. As we will see in our two most important quantum algorithms later part of the course, the Grover's algorithm and the Shor's algorithm, they can all be viewed as a kind of a quantum query algorithm. Okay. And yeah, so quantum query complexity, because you have this very information structure. So whenever you do query, you do this very fixed black box here. Okay. So there are a lot of tools that you can bound on the query use. Okay. So yeah, it's much easier to think about quantum query algorithm than just a general quantum algorithm. And in particular, it's easier to get lower bound. And also, when you get the lower bound on your quantum query complexity, it's basically get a lower bound on your time complexity. Okay. And yeah, we see that this phase version of a quantum oracle, this phase K-back trick is very useful. You can only for quantum oracle you can convert it to this phase version of the oracle. So you have this -1 to your function. Okay. Then I guess yeah, but this is a bit different from just the phase kickback we do because we also have control here. And when you think about the whole problem a bit harder, you see that this control is necessary for your face version to convert back to your original version. Okay. And yeah, let's now, so this is from this time, we have quite a bit of review, okay, and now start talking about something new, okay, and let's compare a little bit about classical and quantum query. So as we say, classical query, I guess it's not really you here, but in classical circuit, we can also think about the black box. But then classical black box, you can just do it this way. Because classically you don't need to be reversible or anything, so you can just have your x and you compute f of x. Okay. And but quantum query need to be reversible. So in addition to being how should I say? You can do quantum superposition. You also need to have a separate input and output register. So you have an input register that write your x, and the output register that will write f of x here, and will plus whatever you original have on this y register. And I will see that this O plus thing is give us a very nice property, because this O plus thing here is what give us a ability to do phase kickback. So yeah, so you see that with a different y here, and in particular when you have a quantum superposition of y here, we can do some really really incredible quantum trick with this quantum oracle. Okay. And yeah, both this thing here, so we need to keep track of x here for this gate to be reversible. Okay. And we have some comparison between classical and quantum query, and so we think about the power between quantum query and the classical query. So this is a bit of a complexity theory. Yeah, it's easy to see that one quantum oracle code is more useful than one classical oracle code. So because so what a classical oracle code can do is you can compute f of x on some x. If those are classical wire, then you just compute f of x on some x. And to do that with the quantum oracle, it's very easy. You just put y equal to 0 here, and put x here, then you can get your f of x here, and you can forget your x, just don't use it. Okay, and yeah, so whatever you can calculate with some number of classical oracle code, you can do it with quantum oracle. Okay. And but the big question in quantum complexity theory is, well, I guess in quantum computation we always ask what are the possible quantum speed up, and a nice way to characterize this question is to ask in quantum query complexity. So you can ask all sort of query ask question on all sorts of query problems, and we ask what are the possible gaps between quantum query complexity and classical query complexity. Okay. And yeah, also we will ask so what's the largest gap, and in more general we ask when will we have quantum speed up, so when do we have a gap between quantum query complexity and classical query complexity. And in this language we can this is I guess this is a more formal way to say our previous three results. So in our Dirichlet algorithm, Dirichlet algorithm, and the Bernstein-Vazirani algorithm, we can all say they have a gap between quantum and classical query complexity. So in Dirichlet algorithm, we say the quantum query complexity is 1 and the classical query complexity is 2. And yeah, so let's go back a little bit. Maybe, oh, sorry, not this way. So maybe around here, yeah. So Dirichlet algorithm, we say quantum query complexity is 1, classical query complexity is 2. If you want to do exact, and yeah, and Dirichlet, we say quantum query is still 1, but classical query is depend on your model. Classical query is is 2 to the n minus 1 if you want to be exact. And but just a small constant if you can allow randomized algorithm. And then in Bernstein-Vazirani algorithm, quantum query is still 1, quantum Curry complexity is still 1, but the classical Curry complexity is n. Okay. And finally we go to our new algorithm today. Okay. And I think we can just finish this and but this is quite long. Okay, so we do our Simon's problem. Okay, so this is our latest quantum algorithm of this slide. We have the 7 problem. So that's solved by Simon's algorithm. Okay, so this is still a very very, how do I say, kind of an unnatural problem, but it's constructed to show that there is a big separation between quantum and classical Curry complexity. So the problem is we have f equal to 0, 1 to n to 0, 1 to n. Okay, so now f is even more general than Brazilian and Larani. So f is not even a Boolean function. So it has n bit input and n bit output, and those two n are the same n. Okay, our oracle is quite complicated, and I guess we haven't defined oracle on this, but it's not too important. But let's go to the algorithm part. So the oracle we define for n bit output is like this. Okay, so we also x, y, and y o plus f. And here we need to define what is O plus when y and f of x are both n-bit string, and we define it as bitwise, basically bitwise XOR. So on every bit we do XOR between y and f of x. Okay, and so let's write it here. So our u will have just copy it here. So our UF will do this thing. UF, we have x and y, and the output will be still input is x, and output will be y o plus f of x, and y o plus f of x is bitwise XOR. I guess this is a bitwise addition, and this bitwise addition we have a little bit down here. So so when we have a string, this is a bitwise addition, means that every bit we do XOR. Okay, and so we define oracle this way, and okay, and now we have a promise on our f. Okay, so f is this huge function, and and there is once again a secret, and there is a secret s, but this secret s don't totally depend on f. It just restrict f in some way. Okay, so there is this hidden s that kind of pairs between different input of f. Okay, so f is actually a 2-to-1 function, and okay, so here maybe that's right here. So maybe f is 2 to 1. Okay, so f is a 2-to-1 function, and the inputs of f are paired together in this weird way. So they are paired together if only if y equal to x o plus this secret string. Okay, and and because you want x, y to be different, so this secret string actually cannot be anything. So in particular, it cannot be this O0 string. Okay, so so we have this special restriction on f of x equal to fy if only if y equal to x or plus this s. Okay, and so this is 2-to-1 because then this relation will pair together just 1x and 1y. In particular, you have y o plus this is a different thing. So in particular, so if you o plus once again, then you will, so you have y o plus s, then we'll get back to this x. Okay, so it's written here. So this is this relation is symmetric between x and y. So because y o plus s equal to s x o plus s o plus s, And but this bitwise addition is associative, so you can have SO plus S first, and everything bitwise addition with itself equal to 0 string. So it back to this X string. Okay, so far good. Make sure we understand what this question. This this setup. Okay, and yeah, so this F has 2 to the n-1 pairs. And just like before, our problem now is find this secret string S. Okay, and here we have some example. Okay. And for example, we want to find this S, and for some n equal to 3f. Okay. And for classical algorithm, it's easy to show that the best way to do this is the best way to do this, because this S is totally random, is you want to find a pair that has the same output. Okay? Because f of x and f of y can be really anything. They only have constraint when you hit the x and when you hit this so-called collision on the input. So only when your y equal to x o plus s you get any information. So the way to solve this problem is you just pick a random input. So you take f of 0, 0, 0, 1, 0, 1, 0, 0, 1, etc. And until you hit some collision between the input. So here we see in this example our f of 0, 0, 1 and f of 1, 1, 1 are the same. And just for simplicity, we write the outcome with from number 0 to 7 instead of the 3-bit. Okay, just because it's shorter, but really it's 3-bit to 3-bit. And anyway, we see that f of 0, 0, 1 and f of 1, 1, 1 are the same. Then we know 0, 0, 1 and 1, 1, 1 are paired together by this S. And from here we can calculate S. S is just you can just do bitwise addition between x and y, and it should give you x S. Okay, so because y o plus x is y equal to x o plus s, so I guess I should write this in different order. So this is x o plus s o plus x, and yeah, but this is then we can switch order. I guess yeah, I guess we switch order in first, doesn't matter. So this is I should write x plus y is a bit nicer. Okay. So if you have x plus y, then then we have x plus s, and then we have twice of x plus s, but twice of x equal to 0 when we are matu, so this is just s. Okay, so we add together those two strings, and yeah, so we see this is 1, 1, 0 because we do bitwise addition. So we have 0 plus 1 equal to 1, 0 plus 1 equal to 1, and 1 plus 1 equal to 0. Okay, and yeah, so this is Simon's problem. Any question on the problem setup? Okay. And I guess we are halfway through the classical algorithm. And as we said, classical algorithm you just find trying to find random input until you find a collision. Okay. And now the question is how many of those inputs you need to pick in order for you to find a collision. Okay. And there is a slight trick here, so you might be a little faster than you think. Okay. So if you have just two input here, then the probability of the collision is well basically 2 to the n, basically 1 over 2 to the n. Okay. But when you have a lot of them, you only need the square root of 2 to the n of them to find a collision. And this is the thing of this comes from so-called birthday paradox. Okay, the birthday paradox says that if you want to find two people that has same birthday with probability 50%. Okay, so birthday there are about 365 days. Okay, if you want to find two people of the same birthday, you will just pick two of them the probability is basically 1/365. But if you have a lot of people, then you only need 23 people to have probability 50%. And that's because the number of pairs is more than number of people. Okay? Because you have 23 people, then you have 2 to the 53 pairs between those people. And yeah, so you calculate the probability of all 253 pairs non-collision, then it's about 50%. Okay. And so in general, you have you take n random sample, then n random sample in this kind of thing, then you will get order n square possible collision, and yeah, so you can find the collision or probability about 1/n squared. Okay? And you can calculate the detailed things in your homework. But the short answer we want here is that for Simon's problem, classic algorithm, you need about square root of 2 to the n. Okay, you need a theta square root 2 to the n number of queries to find the collision. Okay, so that's Simon's problem. And for classical query, okay, so there is this weird square root from this birthday paradox, but but you see that this is still quite exponential here. So this is exponential in basically smaller coefficient. So it's about 2 to the n over 2. Okay. So this kind of thing we still think is exponential. It's 2 to the this is 2 to the order n. Okay, or 2 to the theta n. Yeah, and yeah, so that's Simon's problem in terms of classical. And now let's try to do this with quantum query algorithm. And here I guess we don't actually use phase kickback here. We do something a bit funny. Okay, so this is our algorithm for Simon's problem. And what we do is we'll run this quantum circuit here. So here you see a quantum circuit. We'll do this many times, and once again do some classical post-processing. So the measurement result here will not just give you S directly. Okay? So we'll do several of these and do some actually probabilistic classical calculation with the result we get here. So we run this algorithm, this circuit here, and get some result Z here. And from this several of these results Z, we can solve our Simon's problem. Okay. But let's first look at this algorithm here. So once again, it's quite like a George Josa. So we have our oracle here, and headmark to n as input, then headmark to n on this input register, and measure it. But here we don't have phase kickback, we just have a 0 to n here. And so basically this y is nothing, and we just have f of x here, and yeah, and we throw away this, but we can think about doing measurement here, because the principle of implicit measurement. Okay. This is where we see the principle of implicit measurement give us some nice analysis. Okay, and yeah, so let's see how this goes. So we have a superposition of our input here, and then we go through the quantum oracle. Then we see that we have a superposition of all the input and all the output. Okay, and yeah, so this is our side 2. And if you just measure everything on side 2, then we know that this is not very useful. This is not more powerful than classical algorithm, because you just get a random x and a random f of x, and you can just do that with a classical query by query a random x. Okay, but yeah, but we see that in Simon's problem, because we do this headmark to n here, we do some weird interference on our input register, we actually get better information on our secret string. Okay. But anyway, so let's try to go through the algebraic analysis here. We have side 1 and side 2. This, so far it should be not too hard. Okay, and yeah, so this is bitwise addition here, but it's actually not too important how we do the addition here, because y is all 0, we only want we have f of x here. Okay, and yeah, so we have this thing, and now we do our principle of implicit measurement, because this register is not used, so we might as well measure it. And because we never do any interaction between this wire and this wire, so we might as well do measurement before we even do the head mount. Okay, so let's see what happens when we measure the second register. Okay, and I guess now an important thing is this is different from, so only measure the second register is different from measuring both registers. Okay, so this is something we tested on our meter. Okay. When you measure the second register, you get something really interesting. So you will get to learn your f of x. Okay, you learn your f of x, but you don't learn which x give you this f of x. Okay. So on the second register, you will learn f of x, and it's 1 for f of x, and f of x, as we know, there are 2 to the n minus 1 different things. Okay, so you will get 1 of them random because you have all the superposition of them here. So you get 1 of the 2 to the n minus 1 of f of x, and but the x part you didn't do measurement, so they are still in quantum coherence. And so what happens is you will get both possible input of x here correspond to your f of x. Okay. So this side 3 here, so this is important part of the analysis, is that you will project onto, so after getting your outcome being some f of x, let's say the outcome is on D, so D is one of the possible 2 to the n minus 1 outcome. Okay. So get some D, and then on the first register you will get a superposition between x and xo plus s, or x and y, where f of x and f of y both equal to D. Okay. So after getting outcome being D here, you get x being the superposition of the 2 pure image between D, 2 pure image of D. Okay, yeah, you can do this. You can also do this more careful, because you know when you do measurement here, you are projecting onto all the possible outcome here. So you project onto the possible outcome on the second register, and tensor identity on the first register. Okay, so yeah, so this is a projection property. Although technically we don't need to do this here, but this makes the analysis much easier. Okay, because now we don't need to write this summation here. We just have some particular x, and plus is secret pair. So x plus the xo plus s. Okay, so we see that from this thing we get quite a bit of information on s. Okay. So if we have several copies of this thing with same s, then we can know the answer. But unfortunately, we cannot get that, because every time we do this thing and measure side 3 here, we get a random D. And so that's why we need to do this weird head map here. Okay. So we have this side 3 here, but we don't know x, so we cannot quite get just s here. But we can actually get s out of this weird step by doing the head map and measure. Okay. So we do side 4. Okay, and now here we need to do brute force calculation. So we need to apply our head map formula. So now we need to summation over another variable z, and we will have our phase being -1 to the x dot z plus -1 to the, now this is x plus s dot z. Okay, And yeah, so we have this weird coefficient in front of z. Okay, and yeah, so this thing is a plus minus 1, and this thing is a plus minus 1. And we want, well, now we want to, just like in previous analysis, now we want to see, well, here we have a lot of possible z, and we want to see what kind of z actually has a probability getting measured here. Okay. And that those z that has a coefficient being non-zero. Okay. And we want coefficient to be non-zero, then basically we want this thing and this thing to be equal to 2. Okay. Because if they are different, then this minus 1 and this minus 1 will cancel out with plus 1 and minus 1. Okay. But if they are different, then they are both minus 1 or both plus 1, and this will be non-zero. Okay. And so so if they are non-zero, then x dot z should equal to this x plus s dot z. Okay. And then miraculously we see that the x part cancel out. So x is something random, and we don't know x, so we really cannot do any computation on x. So it's better that they cancel out. Okay. And yeah, it's really nice that after we do this HEDMA, then this condition of non-zero amplitude, the x dot z part just cancel out. So we see that the non-zero amplitude comes from where s dot z equal to 0. Okay. So s dot z equal to 0, and now this is something nice. So now this gives us the information about z. Okay. And if you do calculation a bit carefully, you see that all the z with non-zero amplitude will have actually the same amplitude, because the calculated analysis is very easy, because it's actually either plus 2 or minus 2 here, and the calculated probability is the same. So every z with non-zero amplitude here has the same probability of getting measured. So we will get a random z that has s dot z equal to 0. Okay, and yeah, so this is how we get the information on s. Remember, our goal is to calculate s. Okay. And yeah, so our goal is to calculate s, and what we get from our this small quantum circuit here is we get a z that s dot z equal to 0. And then this part of this analysis, we just can kind of wavy, and we say we will get so we just run this over and over again. We get a whole bunch of z such that s dot z equals 0. So we get z1, z2 to zk, etc. Remember, they are uniformly distributed. And yeah, and then we just solve a linear equation from those z1 to zk. So we think s as a nb string, so it has a small n different variable, s1, s2 to sn, and you can list all those s dot z equal to 0 as a linear seesaw equation. And yeah. Okay, and then you can find s when your linear seesaw equation is I want to say non-singular, but it's going to be singular, because this is a homogeneous equation, and we want a non-trivial s here. Okay. But anyway, we want to have n-1 linear independent equation, then we can single out what our s is. Okay. And here we skip over a bit of a probability and a linear algebra, but because your z is uniformly random chosen, so you can show with some linear algebra and probability. If you draw about order n different z with high probability, you can find a unique s from solving this equation. Okay. And yeah, so Simon's algorithm, even for quantum, there is some success probability, because you need to be lucky on drawing, or you need to be not too unlucky when you draw those z. Okay? So you draw enough z, and then you have a very high probability that you can solve for unique s from those linear system equation. Okay. Yeah. And yeah, so that's our result. We can use order n queries to find s, and with high probability. Okay, and yeah, so that's our quantum algorithm for Simon's problem. And in the next minutes, we will show this summary of all the algorithm we shown so far. Okay, so we have Dirichlet's algorithm, Dirichlet's algorithm, Bernstein-Vazirani algorithm problem, and Simon's problem. And Dirichlet's algorithm, we ask whether f(a1) equal to f0. So this f is, I guess we should have a column list f. So here f is 1 bit to 1 bit. And then we have Dirichlet's algorithm, f is n bit to 1 bit, and as f is balanced or constant. And Bernstein-Vazirani algorithm, we want to f is n bit to 1 bit, and is promised to be s star x with some secret string s, and we want to find the secret string s. And the Simon's problem, f has those hidden collisions, so f is actually n bit to n bit, and yeah, and there is this hidden matching parameter s here, and we want to find this s such that when x equal to y0 plus s, f of x will equal to f of y, we have this collision. Okay, and we can see the separation here. So quantum query complexity of those three questions are, and I guess we didn't write a notation, but this is quantum query complexity, and this is all those three are 1, and in Simon's problem this is all 1. Okay. And but I guess this one is a bit different. So all those three are exact, but this is with error. This thing is actually a different complexity. So this is with a small error probability. Okay, and so this one is with error probability. Okay. Error probability, and for classical, we have a rough distinction between deterministic algorithm and randomized algorithm. So for deterministic algorithm, Dirichlet's algorithm, we need 2 query, and random algorithm also need about 2 query, and Dirichlet we need deterministic, we need about 2 to n minus 1 plus 1, but random algorithm only need 1, so there is no separation between this and this, but we have an exponential separation here. And yeah, we're almost out of time. And for Bernstein-Vazirani, deterministic is 1, and the randomized is also 1. So this is the first separation between quantum and the randomized. And finally, Simon's algorithm, we have exponential separation between quantum and the randomized. So randomized is 2 to the n over 2, and quantum is okay. And yeah, remember those 2 results. So how to calculate n-bit headbar is this sum over z minus 1 to the x star z, and normalization, and also this phase kickback trick is very nice. Okay, and yeah, sorry for going over time. And next time we should start on our journey of phase estimation and Schwartz algorithm. Good. And yeah, so see you on Thursday. Okay.